Yeah. Hi, everyone. Hi, welcome to the Hitchhiker's Guide to Rheology webinar. And today the speaker is Kindness. She will talk about impact of viscoplastic drop. And she comes from Paris actually, not Paris Tech, at CMF. And we are really happy to have her right now. And you can start to share your slide, Kindness. And thank you for being here again.
Hey, well,
Yes.
I'm glad to be here. Thank you, Leah and Michelle, for this. It's really an amazing platform to
Maybe Kindness
share.
before you should be able to share yours. Oh,
Yeah.
great. Yeah.
I hope you can see it now.
Yeah.
Oh, no.
Maybe you can tell us a bit more about yourself and where did you study and more information about your past.
Well, that's a funny question about my past. Like shady past or something. But yeah. Anyway, I'm a third-year PhD student from Paris, just like Leah said. And before now, I did my master's in École Centrale de Nantes on computational mechanics. I also did a specialized master's in Paris on advanced modeling. Before that, my bachelor's was from Nigeria. I am Nigerian originally, and I studied mechanical engineering. So basically, it's all related, right? Mechanical engineering, mechanics, and well, I've been basically one directional, no much fuss about it. Yeah. So right now, I'm at the end of my PhD, basically. So super stressed, super anxious, everything, feeling everything at once. So yeah, bring it on.
Thank you. Yes, that's
Thank
gonna
you.
be fine.
Okay. So, wait, I don't know if this is better. Let's see. Okay, so maybe this is better. So yeah, I'm giving, this is actually the broad topic of my PhD thesis, which is the impact of viscoplastic drops. And here in Paris, I'm under the supervision of 4 amazing professors, right? They've been my support and they've been super fantastic. Salmo, Rudy, Ellie, and Roma. Okay, so everything I know, it's on them. If I'm wrong, it's also on them. Okay, so let's start first by describing what viscoplastic drops are. Basically, these are fluids that have a characteristic stress value. So for deformation levels above this stress level, they deform like elastic solids. But rather for deformations below this stress level, they deform like elastic solids, right? Limited deformations. But if the stress level is above this stress level, they flow just like viscous liquids, right? An example here is given for mayonnaise. If we notice this is the column of mayonnaise drop falling, we notice the bottom part that deforms like it flows like a liquid. And the top part here that basically retains its shape, acting like a solid. Now, in the more general sense, they are called elasto-viscoplastic fluids, but under some flow conditions, the elastic properties of these fluids are not negligible, and so we call them viscoplastic drops. And this is the case for the fluids I will be discussing here. Now, the source of these microscopic properties of elasticity, viscosity, plasticity that we see in these fluids can be related to what goes on in the microscale. So we could talk about intermolecular forces of attraction, the capillary bridges, friction. All of these translate in the macro scale as yield stress or a strain rate dependent viscosity. And there are a lot of fluids that actually behave like this. I've mentioned mayonnaise, we have ketchup, we have our toothpaste, we have peanut butter, even our blood have these complex properties. And the truth is, these fluids are widely used in the applications that will be mentioned here. For instance, here we see 3D printing, right? One of the questions in such application is if we can control the spreading of these fluids, or if we can control the shapes that arises from the spreading. Another application is in the application of herbicides in agriculture or the production of aerosols and all of that. This is one of the major applications of my study, where I'm studying the impact of these complex fluids, viscoplastic drops. And to do this, I studied these fluids in different flow configurations. First, the impact of these drops on a solid, a sticky surface, right? Hydrophilic. Then we have a PS solid here. Now, one thing is that all of these configurations allow us to explore different physical mechanisms that control the impact and the spreading of these drops. For instance, on the impact on the PS solid is just a plate with a hole. We can see an interplay of extensional deformation and shear deformation. Here on a sticky solid, we see it highlights the effect of shear deformations. One thing that is quite different here, on the top left here is the impact on the solid. On the bottom right is the impact on a gas layer. We notice these are two similar drops, same flow conditions, but we have different spreading levels reached. Again, these different flow configurations allow us to explore the mechanisms that occur for the impact of these drops. Another interesting thing to highlight is the fact that for the impact of these drops, we can also highlight the fact that we can get or modify the shapes of the drops as they impact, as we see for the impact of the drop on a liquid bath here. So basically, my thesis covers these 6 different flow configurations. And for the purpose of this talk, we'll start simple, right? We'll start with the impact on the solid. And then I would also like to highlight the impact on the gas layer. There are 2 very similar configurations, but yet we'll get some differences. Okay, so let's start with the impact on the solid. So here is a ketchup drop, right? Impacting on an acrylic plate. And we notice first, it falls with an initial kinetic energy, and then it spreads, and then it sticks to the plate when it gets to its maximum spread. Now, let's see why we decided to study this. First, this is a slide that shows the differences between the impact of Newtonian drop, here water, and a viscoplastic drop, bentonite. Bentonite is just clay particles in water. Okay, it's a dense suspension, clay particles in water. So just by increasing the mass percentage of bentonite particles in water, we increase drastically the yield stress of the fluid. Well, I mentioned earlier that this microscopic property of yield stress is related to what happens in the micro scale. So the particles in bentonite basically form like a house of card-like structure, right, in clusters. And the more of these particles you add to the suspension, they form a jam structure, so that you need a lot of energy to break this structure. And then, of course, the surrounding fluid gives a viscosity to the suspension when it is deformed. So it is reasonable that as we add more particles of bentonite in our suspension, this energy or the strength you need to break this structure would increase. And that's why we have this increase in the yield stress. Something to note is the fact that as we increase this mass concentration and also the yield stress, the shape of the drop changes. So surface tension-induced deformations are impeded by yield stress. So we no longer have spherical drops, which is a signature of surface tension, trying to keep the minimum surface of an object. But yield stress overtakes the whole thing, and the drop retains the shape of whatever nozzle is coming out from. Something else we notice is the spreading dynamics also change as this happens. So we see that even these instabilities that occur during the spreading of water are also non-existent for the spreading of this viscoplastic drop bentonite. So it necessitates a question: can we predict the spreading of such complex fluids? Can we determine the shapes? Can we predict the maximum spreading, the spreading dynamics in general? And this is what we do here. So there are little works discussing this, but we can mention the nominal work of Lu and Forte. So they described that for a viscoplastic drop, which can be defined using a Herschel-Berkeley model, that if the drop has the same Reynolds number and plastic number as defined here like this, then we would have the same relative spreading level. Well, it's okay. And this has been proposed, and let's see if that works basically. So we started easy. We took bentonite again. We tried as much as we could to get spherical drops, basically aspect ratio equal to 1, right? And then we watched how it spread. We calculated a relative spreading level here. And then we took another drop just by increasing the volume of the drop, but it's still spherical, aspect ratio equal to 1. And again, we got the same spreading level. Theory works, right? But then again, we increase the volume again, but now just by modifying the shape of the drop. And what happens? Well, we get a different spreading level measured. And obviously, this is not something that has to do with the volume, because we tried spherical drops with 2 different volumes and we got the same spreading level, right? So definitely has to do with something that has to do with the aspect ratio, the shape of the drop. And this is what we try to investigate here. So to do this, we use experiments, we use numerical simulations, and we also propose a physical formulation that is able to capture the dynamics of the flow. And this is what I'll show next. Basically, drops are centimetric or millimetric drops. And what we want is to capture the spreading. So this is basically the governing equation of this entire problem. So our drop falls freely with an initial kinetic energy, like I stated earlier. And during its spreading, some of this energy is dissipated either through viscous work or plastic work. And then, of course, it spreads, surface energy increases, so we have a surface temp here. What happens if we modify this equation? We basically rearrange it. We're not adding anything or removing anything. We're just dividing each term in this equation by the driving force, which is the kinetic energy. And what do we get? We get a dimensionless form of this equation. And we see the dimensionless numbers that control this problem are emerge naturally, which is the Reynolds number here, the plastic number, an aspect ratio. Of course, we have a Weber's number, but for now, we're going to neglect this, and we'll explain why later. So basically, we have 3 dimensionless parameters that control our flow: the Reynolds number, the plastic number, and our aspect ratio. Okay, so for the numerical methods, thanks to our numerical simulations, we're able to test the different shapes for the drops, right? Cylindrical, prismatic, prolate drops. And we basically, our code is equipped with adaptive mesh and level sets that we're able to capture the interfaces as our drop deforms. We implement the finite element method, and we describe our fluids as Herschel-Berkeley fluids using a regularization term, the Papanastasiou regularization. Basically, it's just a cutoff strain rate here that bounds our viscosity for very small values of the strain rate. Okay, so we don't have a simulation that explodes, basically viscosity going to infinity. So it's a bounding factor. Okay, so parameters for numerical simulation, different shape of jaws, a range of fluid parameters. Experimental approach is quite simple. We have a camera, we have a pump nozzle system that generates the drops. We have a light system. Our camera is able to follow the drops as they spread. So we measure the initial shape of the drop, we measure the velocities and the final shape of the drops. Again, for experiments, we explored a wide range of fluids, right? Alginates, bentonites, carbopol, ketchup, mayonnaise. This allows us to explore, gain a wide range of rheological properties, and we're sure that our numerical simulations are right. We have experiments that will validate our work. Okay, so something else to note is the fact that I mentioned earlier that for these fluids, the elastic component of our drops are negligible, and so they are termed viscoplastic fluids. And you get this using some dimensionless parameters. One popular one we might know is the Deborah's number. Basically, it compares the characteristic realization time of the fluid to the time of the flow. And if this number is way smaller than 1, then we can say it is inelastic, right? We can ignore this elastic property of the fluid. And again, another reason why the Weber number initially that gives the effect of the surface tension is neglected is, again, through this capillary number here. So it's way larger than 10, which gives us which gives us an idea that this surface stem can be neglected. But again, would show more results to prove or to validate our hypothesis here. Okay. So going to the results. So remember, for experiments, we started with 2 spherical drops, right? We did the same thing with the numerical simulations. So basically, one thing to note here is this these drops from the second drop to the 5th. The left side gives the velocity contours, and the right gives the regions of the yielded and unyielded regions, basically the parts that flow and the parts that act like solid. Okay, so for the spherical drops, the first one, notice the size of the drop. Okay, and moving from A to B, we only increase the volume of the drop. It's still a spherical drop, but the volume is increased. Okay, and we measured the same spreading levels, just like our experiments, just like the theory. So if 2 drops have the same Reynolds number and plastic number, they will have the same spreading level. But what happens again, if we increase the volume, we modify the shape of the drop. We're increasing the volume just by modifying the shape of the drop. And just like our experiments, the current theory does not hold. We have another spreading level. Okay, from C to D, we're reducing the volume, but keeping the same aspect ratio, the same shape. And we have similar spreading levels, same spreading levels. Okay, so again, this is not a volume effect, but it's something that has to do with the aspect ratio. And thanks to our numerical simulations, again, we're able to understand why this is so. So basically, we will notice that even for the spherical drops, despite the volume, we have the same flow dynamics. But between the spherical drop and the pleural drop, these dynamics change. We have a higher percentage of the, or a higher ratio of the drop as unyielded. Think about a crash test, basically. So you would have that most of the deformation will be localized at the bottom or at the part closest to the obstacle. And this is why we have higher relative spreading levels. These localized deformations at the bottom of the drop. Again, this gives us, our numerical simulations are giving us insights to explaining why the current theory does not hold, that if two drops have the same Reynolds number and plastic number, they should have the same spreading levels. So we did it again, we did the same exercise. Basically, we took drops again with the same plastic number and Reynolds number. For the spherical drops, we have the same spreading level, but for the prolate drop, we have higher spreading levels. Again, because the dynamics change, we have a localization of the deformation at the bottom of the plate, and so more spreading. So given this agreement between our numerical simulations and the experiment, we go further. And one of the tools, again, we use is the energy budget analysis. So we basically quantify each energy term that is present during the impact and spreading of the drop. And remember, this is the kinetic energy, and then our dissipative terms, which could be either the viscous or the plastic term. We have a surface energy, and well, we have a gravitational energy term, but it's negligible, as we'll show in the next slide. So basically, this is a slide giving the energy quantities, right? So remember our flow formulation. The kinetic energy in blue here, it decreases as the drop spreads. And then while it is spreading, the energy is dissipated or converted to surface energy. Notice the green curves here are close to zero, basically, and those are the gravitational terms, so they are negligible. We had good reason for neglecting it. Also notice the gray curves, which are the surface energy terms, right? For all of the curves are also marginal. So we had good reason initially to ignore the capillary term. So surface energy is not playing a dominant role during the spreading of these drops. Now, to describe these charts, let's focus on these parts, the top right, basically. So notice the Reynolds number and the plastic number. Moving from D to F, we're increasing the plastic number. So basically, we're increasing yield stress, right? So on D, we have the kinetic energy that is completely dissipated through the viscous term, the orange curve here. So we have sort of an interplay between the kinetic energy, inertia, and viscous dissipation. From D to E, we've increased the plastic number. So we've increased the yield stress of our fluid. And we notice that the black curve, which is the plastic dissipation term, has increased, almost comparable to the viscous dissipation term in orange. Moving from E to F, further increase in the plastic number, and we see an overshoot of the black curve, the plastic dissipation term, overshadowing the viscous dissipation term. Again, we see similar trends for all of these curves. One thing we should notice is, okay, the top right here and the bottom left here. If we notice, their volumes are the same, but the shapes are different. So moving from a spherical drop to a polar drop of similar volume, but we notice slight increase in the plastic dissipation term. If you notice, you can see clearly in the middle curves, E and H. Again, is related to the fact that for the prolate drops, the unyielded region is higher. And so this implies more dissipation through the plastic term. So already these energy curves are giving us an idea of spreading regimes impact spreading regimes. So we can have a regime that is completely dominated by the viscous dissipation. So our kinetic energy term is dissipated completely through viscous work. And then we have a regime that is dominated by the plastic dissipation, right? And then another regime where there is a mix of both the viscous and plastic dissipation, so a mixed regime. So given these ideas, basically, we can come up with scalings for these regimes, these impact spreading regimes. And that's what we do next. So basically, for the inertial viscous regime, we have an interplay between the kinetic term and the viscous term. And just by using the right hypothesis, we get a scaling for the spreading, for the relative spreading of our drops. Notice that all of these terms are things that you can compute a priori before the experiments, before the simulations, so you can predict the spreading levels of your drop, right? So for the viscous scaling, it is related to the Reynolds number and an aspect ratio. Again, we can do something similar for our plastic scale region, so the inertial plastic region, where our kinetic energy is dissipated through the plastic work. And we get a suitable scaling for our spreading. And remember, we have a mixed regime, basically, right? So this occurs when both of these terms are equal, basically an intersection of the inertial viscous and inertial plastic regime. And we can get a generalized number that determines the regime of our impact event. And this is what we call the impact number here. So it's possible to plot now our relative spreading levels against this impact number. So what happens when we do this? So we have here simulations for different drop shapes. So a prolate drop of aspect ratio 4 and a spherical drop. And because you notice on the scalings here that there is no aspect ratio treatment, we have the points do not collapse, basically. We do not have an agreement for the flow dynamics, right? Again, if we add experiments, it even becomes worse. But what happens when we add this aspect ratio treatment? We bring in our aspect ratio terms into our equations as we have proposed. And we see a nice collapse of the points across a master curve. So this effect of aspect ratio on the impact of viscoplastic drops on solids is not a trivial issue. It actually has a lot of effect on the spreading level predicted and also on the regime of the spreading. Okay. So again, we can propose a generalized master curve like this, which includes the experiments and numerical simulations for which we can predict the spreading levels and also the impact regimes for our fields. And again, these parameters are things that can be computed a priori. So before our experiments, we can predict the maximum spread of our drop. So these are what I just presented, results gotten from our published paper in Journal of Fluid Mechanics. And if you want details on that, please do go assess that. And let me know your feedback. I'll be glad to hear from you. So I would stop briefly here to maybe get questions on that part of my talk, if possible, please. Or was I missing any questions before?
Yeah, do not hesitate if you have questions. I don't know if the audience, you can directly talk or write the question in the chat. No, I don't think.
Okay, then.
I have just one question. Have you looked at the size of the particle in the suspension and how it can affect your flow?
The size.
Yeah.
So What do you mean? So the particle size is about 5 microns.
Okay.
Okay. So basically it's all bulk rheology for me. I don't go to
You never go
particle.
to particle.
Yeah.
Okay.
Yeah. So they're all bulk properties that I measure.
Okay. Just to know, because if there was like maybe bigger particles, it would have been
Mhm.
something like also some dissipative energy through this kind of when you have your drop that is flowing, and if you have large enough particles, it can affect also the flowing, just like a squeeze test. Whatever. It was my question.
Okay.
Thank you. You can for sure, and maybe at the end of the talk, people will type.
Leah, you reminded me of the first speaker we had
Yeah.
here.
Okay.
Okay, yeah, thank you. I mean, you can,
You
if
can
there are
finish.
no more questions, you can just continue.
Okay then. So this part of the talk talks about the impact of viscoplastic drops on a gas layer. So basically this is coming from the Leidenfrost effect. I don't know if we're familiar with it, but we should be. So basically for the Leidenfrost effect, we have a drop, a cold drop that comes in contact with a solid that is way hotter than its boiling point, such that when it comes so close, it evaporates and forms an insulating vapor layer around the drop. And this makes the drop not to evaporate as fast as it would have. We see it usually in our kitchens, right? We have a pan and a super hot pan, and we put drops of water on the pan, and then we see the drops skittering across the pan. And normally the water should have evaporated if the pan is not as hot as the Leidenfrost point or hotter than that. If it was even a little bit cooler, would have the drop evaporate quickly. And this is an effect that is quite useful, I think, in casting processes. Now, for this study, it's the inverse of this. So basically, the drop here is hotter than the surface. And the good thing is, because of that, it is not the drop that evaporates. So the volume of the drop is conserved. We're not losing any drop particles, right? It's conserved. And it is the surface, the cold surface, that evaporates and forms this insulating layer. And basically, because it is insulated, it does not touch the surface of the solid. And so we will have, it will impede the shear deformations, and we would have more spreading than we would have had for a regular solid, right? And this is what we study here. So for this talk, I would like to just use a simple fluid, a Newtonian fluid, to introduce the ideas that were used in studying for the viscoplastic fluid. And this is what I would show next. So basically, like I have described, we have a drop and we have a plate with a very thin layer of nitrogen. This drop, when it comes close to this nitrogen layer, it causes it to evaporate, creating this insulating vapor layer, as we see here. And just like for the previous talk, we are trying to measure the relative spreading level and make predictions to measure this before the experiments, before simulation. So we are trying to get scaling relations for such flow condition. So experimentally, we have this setup. This is a little bit more tricky because now we're working with nitrogen, which is very volatile, but again, try to get a very thin layer for our experiments, and then we let our drop impact on it. So one thing that is quite interesting is the fact this levitating effect, again, because of the insulating vapor layer, our drop does not come in contact with the solid, but rather spreads on that layer. So basically, this is giving us a side-by-side comparisons between the impact on the solid and the impact on this gas layer. And we see two similar drops, but look at this relative the spreading levels attained for the nitrogen gas layer. Okay, so again, this is a new situation for the impact. So we can have a situation where our drop is not our drop spreads so much because of some other physical mechanism that is occurring during the flow, and this is what we want to study. So one thing for the simulations is the fact that this now has a lot of other elements. So we have our plates, we have our drop, we have the nitrogen layer, we have the vapor layer. So how many things are we going to model? What should we model and what should we not model? Trying to reduce computational costs, we're trying to reduce the number of meshes, trying to make our simulations as robust as possible. So an idea would be just to model the fluid and the air as we have done before, but introduce a boundary condition that takes into account the effect of this vapor layer. And this is what we do by introducing an upward velocity. Basically, this velocity is responsible for the levitation of our drop. But again, we resolve the conservation of mass and momentum equations using a Newtonian fluid. Again, this is for a simple fluid, right? To reduce the complexities of the equations I'm going to show next. So how do we model this upward velocity, this vapor velocity that causes the levitation of our drop during the spreading? And this is what we discuss here. So we use heat transfer equations. So the heat conducted through the vapor film is also the heat that is responsible for the phase change, the evaporation of the liquid nitrogen to vapor. And this is very classic. And we get an equation for the velocity. However, we have a term here, the thickness of the vapor film. And this is actually important for us, especially for modeling computational domain. So we need a mesh size that is able to capture the effect of this vapor layer. If our mesh is so big, then we're basically not capturing the effect of the vapor layer. Our drop will just descend and touch the plate, basically, because we don't have mesh size small enough to capture this effect of the vapor layer, and hence this upward velocity. So how do we compute this minimum mesh size, which is related to the thickness of the vapor film? And to do this, we use the lubrication theory. Basically, this is the conservation of momentum equation, just without the inertia terms, right? So, and no source term. So basically, the pressure gradient and the viscous dissipation terms. Okay. And again, added to our heat transfer equation that we derived before, we can get an equation that defines the minimum thickness of our vapor film. And by computation, we got this thickness to be about 10 to minus 5 meters. And using this, we defined our mesh size to be about 10 times smaller than this. And so with this, we're confident that our meshes is suitable to capture the effect of this vapor layer. And to test this basically, so we make a plot of different vapor film thickness to compute the value of this upward velocity, the boundary condition there. And again, it also gives us an idea of the minimum or the maximum distance of our drop at the start of the simulation, and also the minimum mesh size we could use for our simulations. And this is what we basically implement for our numerical simulations. And again, physical formulation, our governing equation for our problems. So we have a drop with an initial kinetic energy falling under gravity. During its spreading, this energy is dissipated through the viscous stem for a Newtonian fluid. So for a Newtonian fluid, there is no yield stress. So we don't have this plastic contribution to the dissipation then. Remember that. And of course, the spreading again would have a surface. The surface is increasing, so we have a surface energy term. Similarly, just as we have done, we divide these terms by the driving force of the problem, which is the kinetic term. And we can obtain the dimensionless parameters that control the problem. And for this case, it's the Reynolds number and the Weber's number. Here we see the Froude's number basically. Again, it is negligible, and this is coming from the fact that we have small size of drops compared to our impact flows. They are negligible. So we neglect the Froude's number here, which gives us an idea of the gravitational term to the inertial term. Okay, so now we have two dimensionless parameters that control our flow, the Reynolds number and a Weber number. So we go for our experiments and also our numerical simulations, and we find a nice agreement between our experiments and numerical simulations. Our simulations, again, are able to capture these levitating effects of the drops we see when they impact on the gas layer. And again, through analysis of our flow fields, we see that instead of a shear flow, just like we see for the impact on the sticky solid just previously, we are having an extensional flow, a biaxial extensional flow. We see that from these flow bounds, the velocity contours here of our flow, of our drops, right? So this is not a shear flow, but an extensional deformation. And so we can go further again, our energy budget analysis, which is a very important tool we use for all of analysis during studying the impact of drops. So for this case, we have a gravitational term, we have a kinetic energy of the drop, we have viscous work, and of course the surface term. And so we're able to quantify each of these terms and see the effect during the spreading of the drop. And this is what is shown here. So basically, moving from A to C on the curve, we are reducing the Reynolds number. So basically, we're increasing the viscosity of our field. So let's say we're moving from water to, I would say, maybe silicone oil or honey or any of that. Notice what happens. So like we said, the kinetic energy of the drop, which is in blue here, the blue triangles, reduces as the drop spreads. What happens is most of this, for this first case here, is converted into surface energy. Notice the red curve is marginal, is very low. So just a bit of this is dissipated through the viscous term. Our green curves, as usual, which is the gravitational term, is negligible. So we do not consider it in our analysis. So moving from A to B, we further reduced we've further reduced the Reynolds number. We've increased the viscosity of the fluid. And what happens? We see an increase in the viscous dissipation term. Still, the surface energy dominates, but the viscous dissipation term is also coming up. So they are almost comparable here, especially at the start of this process, basically. From B to C, we further increase the viscosity. And what happens? We see the viscous dissipation term overpasses the surface energy. So, and again, we're moving from C to D, keeping Reynolds number constant here, but we've increased the Weber's number. So basically, in real sense, we've reduced the surface energy. So think about moving from, say, a fluid like water, right, to a fluid like silicone oil. They are both Newtonian fluids, but silicone oil has a lower surface tension than water. So basically, we, again, are favoring the viscous dissipation, right? We reduce surface tension, favoring viscous dissipation. So again, our energy charts here give us an idea of impact spreading regimes for this drop. So we move from a case where it is dominated by surface energy. So our kinetic energy is converted completely to surface energy, to a case where it is a mixed interplay of viscous dissipation and the surface energy, taking parts of the kinetic energy, and to a case where it is all of the kinetic energy is dissipated through the viscous dissipation, through the viscous work, basically. So, given that our flow is no longer a shear flow, but an extensional deformation, as shown again by these velocity contours, we can propose scalings, again, scaling laws for these relative spreading levels. So for the inertial capillary region, which is that region or that case where the kinetic energy is converted to the surface energy, we can get a scaling for our relative spreading level. Okay, and we see that this depends on the square root of the Weber's number. We can do similar thing for the inertial viscous regime, which is where the kinetic energy is dissipated through the viscous work. And notice here that here our characteristic length is no longer H mean, but D max, because it is an extensional deformation. And again, we can get a suitable scaling for this impact spreading scenario. Okay, so like I said, and just as we've shown previously, there is a situation where both surface energy and viscous dissipation are both comparable. Their effects are comparable. And so this is the mixed regime. And we can propose an impact number for this regime when we equate those two equations we've shown before. And this is the impact number. And coincidentally, it corresponds to the square root of a capillary number, basically. And so, just as we have done our previous exercise, we can propose a master curve like this that takes into account the relative spreading levels and also the spreading regimes. So we can compute these dimensionless properties before our experiments or numerical simulations. And then using that, we can predict the spreading of the drop. And also we can predict what regime our drop after spreading will fall on. Would it be in the inertial capillary regime or the inertial viscous regime? And yes, so with this work, we've again highlighted these regimes for spreading and impact, and also proposed a new scaling for the inertial viscous regime for the impact of drops on a gas layer. And again, this is work, these are results from our work that is being considered for publication in Journal for Fluid Mechanics again. And yeah, well, it took a village to do all of this basically. And there are a lot of persons involved everywhere, and they are super amazing. So the slide goes to every one of them. And yeah, I'm super grateful to them. And yeah, thank you. Thank you for listening. I would like some questions.
Thank you,
if you have that.
Candice. Thank you very, very much for your presentation. I really liked it. Even if I know a bit of your work,
Yeah.
you have way more stuff. I really liked it. Is there any question in the audience for Kindness? Please do not hesitate. Maybe people are a bit shy.
I will break the ice. It's not really a question, but I really liked, so if you can show it again, the video, the first video for the inverse light and frost drop.
Oh.
Like the first video when you see the hot drop coming to the
Yeah.
cold plate.
Here.
Yeah.
This one.
So it's even nice from an aerodynamic point of view because you can see the wake of the vapor around the drop.
Yeah.
You can see the small drops, like small droplets around also bouncing.
Yeah. Then
That's really great. And I just had another question, comment about the next video. There is the video from above where you see the impact of the drop.
Okay, this one.
Yeah, this one. So after the spreading and it comes back, those dark regions is like because it solidifies or
what?
Like,
what dark region?
Well, now wait, like
Yeah.
now those dark regions. What is that?
No, it's just lights reflection.
Oh, just light. Oh, just
Yeah,
that. Okay.
it's light reflection, and basically, so when it expands, we form a rim. At the drop, the edges of the drop are thicker than the middle, basically. So coming back, we have like this thick effect. So it's light telling you the depth, the thickness of the drop. It's just light, basically, effect of light.
Okay. Okay. Nice.
Have
Those
you
are
looked into
very,
this?
very nice.
Have you looked into this instabilities that forms like at the end, this three bubbles shape? Yeah, like very at the end, you can see here that it looks like three circular shape together. And have you looked into it at the end or not at all?
Well, for me,
Yeah.
for this case, I stop at the spreading and also the retraction time, but
Okay.
not these
Not this
shapes are quite
rippling.
random.
Yeah.
They are quite random, basically. So
Yeah.
is this subject for study actually could be to study the final shapes of the drops after impact and retraction.
Yeah, because maybe you can control this pattern at the end and say, yeah, or if you can control the velocity, the rheology of the fluid, whatever, the gas layer and so on, maybe I can predict what will be the shape of the pattern at the end.
True, it's
Well,
possible.
the surface tension is definitely playing a big role here.
Yes,
Yeah.
the surface tension plays a big role during the retraction of the, yeah, definitely.
Great. That's a very, very nice work, Kindness.
Thank you.
Thank you.
Mm.
Okay. Well, people are. Oh yeah, a question there. Go ahead, Tony.
Oh,
it's clapping.
Thank you, Tony. Thank you.
That was an amazing presentation, and it's exceptional. Actually, she's in third year of PhD with like 7 publications.
Oh my God. Oh my God. God. Oh my Thank you, Tony. Thank you.
Yeah, I
Yeah,
must
that's
say that it's
impressive.
impressive. Yeah.
Yeah.
No, really.
So thank you. I guess that either people are shy or simply that was a very clear presentation.
Yeah, it
So
was really clear. And it's gonna be on YouTube, so we can go back into the videos and so on. That is so cool. Thank you so much, Kindness. Thank you everyone for attending Kindness presentation. If you have question in the future, maybe I can give her the question by email or so. So yeah, do not hesitate. Thank you again, Kindness, for being here. It was very, very a pleasure. Maybe Michelle, you can give the new slides.
yeah, you can stop the recording first, maybe.
Oh yeah, I'm gonna stop the recording. Bye. Bye, YouTube.